Hi everyone, today I will go through the analysis of Abalone Age Prediction datasets. First, accurately estimating the age of abalones is important for fisheries management because it helps regulate harvesting and support sustainable marine ecosystems. Traditionally, age is determined by cutting the shell and counting growth rings under a microscope, which is both time-consuming and costly. This project explores whether machine learning can provide a reliable, non-invasive alternative by predicting age from physical measurements. In this video, I will cover three main areas. First is the key data pre-processing and modeling steps. And then we will discover that why the selected models are suitable for this dataset. And finally, there are insights these results provide for real-world applications. First of all, we need to import all of the data and libraries that we need. And then we started to do some exploratory data analysis. The dataset consists of physical measurements such as sex, length, diameter, height, and several weight-related variables. Most predictors are continuous, making the dataset well suited for regression models. And then we do some checkings for the duplicates and missing values. And we can see that this data set is relatively clean. And then to better understand the structure of the data set, we generated some visualizations. These visualizations reviewed strong positive relationships among physical measurements, such as length, diameter, multiple weight-related variables, suggesting that the abalone growth follows a consistent biological scaling pattern. However, several relationships displayed mild curvature rather than perfect linearity, indicating that overly simple models may underfit the data. Then, in terms of the extreme values can actively affect model stability by increasing variance. So, identifying them early is an important step in building reliable predictive models. To improve model robustness, Taki rule based on the interquartile range and the box plot were applied here to detect the outliers. A small number of extreme observations, particularly in height, were identified. Although a few extreme values appeared, they were likely natural biological variation rather than data errors. Also, the target variable is concentrated in mid-range, suggesting that predicting very young or very old abalones may be inherently more difficult. Finally, we also did some skewness of quant analysis. It showed that multiple predictors are right-skewed, meaning that larger abalones are relatively rare but potentially influential during the model training. Because the variable sex is categorical, it was encoded numerically, so it could be used in the models. For algorithm sensitivity to scale, such as k nearest neighbors and support vector regression, the features were standardized to ensure that no single variable dominated the distance calculations. So then we come to feature importance. The feature importance analysis reviewed that shell weight was by far the strongest predictor, contributing nearly half of the model's explanatory power. This makes biological sense that shell thickness increases with age. Other weight variables also ranked highly, confirming that mass-related features dominate geometric ones. Interestingly, sex had minimal impact. Then we comes to the part for model selection. In the very beginning, the dataset was split into training and test sets using an 80 and 20 holdout approach, enabling an unbiased evaluation of model generalization. This validation strategy ensures that model performance reflects how well the model is likely to perform on unseen data. To understand how model complexity impacts prediction performance, multiple supervised learning algorithms were implemented and compared here, including multiple linear regression, regularization models, and tree-based models. Model performance was evaluated using MSE, MAE, and R squared. First, we go with multiple linear regression. Multiple linear regression served as a baseline model. It assumes a linear relationship between predictors and age. MLR achieved 5.1 MSE, 1.6 MAE, and 0.53 R squared, which indicates that about 53% of the variance in abalone age is explained by the model. The prediction scatter plot showed a clear upward trend, indicating that the model captured the overall relationship well, although predictions may become less precise for older abalones. This is because typically MLR has high bias and low variance. It is stable but sometimes may underfit complex biological relationships. Then for regularized models. Here includes ridge regression, lasso regression, and elastic net regression. These models helps address overfitting by shrinking coefficients. Interestingly, ridge performed almost identically to linear regression, suggesting that while some correlation exists among predictors, it is not severe enough to destabilize the model. However, Lasso here performed much worse, with the R square dropping significantly, which indicates that most predictors actually contain useful information. Aggressively shrinking coefficients remove the signal instead of noise. Most predictors actually contain useful information in this case. Then for nonlinear models like k nearest neighbors achieved MSE 5.45, MAE equals to 1.6, and R squared equals to 0.5, being very competitive to multiple linear regression. The KN method captures nonlinear structure but can become sensitive to noise. And then we come to tree-based models like here, decision tree. And we can see it has high MSE equals to 8.61. Decision trees often suffer from high variance. Without pruning or in symbols, they tend to overfit training data but generalize poorly. So in other words, greater flexibility, increased variance without delivering better predictions. So finally, in summary, the results demonstrate that machine learning can provide an efficient alternative to manual age estimation. Potential applications include automated fisheries management, sustainable harvesting policies, and ecological forecasting. The most important takeaway from this analysis is that additional complexity did not translate into better performance. Despite evaluating more flexible algorithms, the linear model remained among the strongest performers. Therefore, effective modeling is not about maximizing sophistication, is it about matching model complexity to structure of the data? Thank you.